Yesterday, me and one of the other teachers were talking about how the beginning of the year we really cared about our videos and we were like editing things and trying to make them real nice. And now, like, none of us care. Well, we care about the videos, but we don't care about editing. She's like, sometimes I just leave it recording while the announcements are playing, and like I don't cut those out. I just put it up. And I've been doing the same thing. I think the other day in chemistry, I made a video and forgot to turn it off. And there was just like 25 minutes of mostly silence at the end of the video. It's all right. They'll live. So if you're seeing this and some of the videos are weird, it's okay. It's part of the classroom experience. You're getting everything that the in-class students are getting. So just a reminder for those of y'all here and those of y'all at home, the homeworks are due at the end of the week on Friday, chapter 3 and 4. So make sure you're working on those. I don't think they're too long, so they shouldn't be too bad, maybe compared to some of the other homeworks. But yes, the homeworks are due, and we will have a test on Friday in Canvas, similar to the other tests that we've been taking. So I need to get that put up, and probably when we're done with this PowerPoint, which will probably be tomorrow, maybe, we will start on the Plate Tectonics lab, which I think is actually a pretty good lab. So we'll see how that goes. So it says, what are the major differences between the lithosphere and the asthenosphere, and how are they each important to plate tectonics? And we might have gone over this slide yesterday, but I just want to start from here because it's a good place. So remember that the lithosphere is the hard, brittle crust on the outside of the globe. The asthenosphere is the semi-molten, hot, kind of like honey consistency layer just underneath the lithosphere, kind of at the top of the mantle. So it's almost like the transition zone between the solid lithosphere and the molten mantle underneath. Oh, the video evidence that, again, my board does not work. I guess I will submit a request because this is frustrating. Does your controller ever disconnect in tournaments? It's not a thing that happens anymore, really. Yeah.
Unless, like,
Your
it's
internet.
low.
Oh yeah, your battery runs out. Yeah. I finally bought a second Switch controller because the battery's still low. So I keep one charging on the console all the time because I don't ever play it like handheld console. I usually play it through my TV. So keep one always charging on the console, and whenever the other one gets low, I just switch them out. All right, so I think we're good now. Yay! All right. So we saw this slide yesterday. Didn't we see this slide? And then I kind of took a break and we looked at the Google Earth images. But it basically shows you the mid-Atlantic ridge right in between North America and Europe, and then gives you a close-up detail of it. You can see the ridge itself. Remember that while these are the longest mountain ranges on the planet, they're not really the highest. And right in the middle, you have this ridge valley. So a valley is kind of the opposite of a ridge, but you do have a valley right in the middle of the ridge, right exactly where all the cracking and spreading is happening, and your magma is coming up to fill those cracks. So they just talk about how most divergent plate boundaries, not all, because we'll talk about divergent plate boundaries on land or continental rifts in a second, but most of them occur in the oceans. And so it's associated with your mid-ocean ridge. There's an elevated seafloor, which gives you your ridge. And then there's also a rift valley right in the middle of it. And I kind of mentioned that they're not very tall, 2 to 3 kilometers, compared to their overall width, which is about 1,000 to 4,000 kilometers wide. So pretty low and wide these surfaces are. So let's see. We talked about seafloor spreading and its rate. I think this is maybe where the last slide that we ended off with. So know that it's an average of about 5 centimeters per year, which is not very much. On the ruler here, 5 centimeters is like close to 2 inches. Looks like almost exactly 2 inches, but I know that's not right. Let me look this up just real quick because I'm curious. Because I thought it was like, what is centimeters to inches? Maybe I'm thinking meters to feet. 5 centimeters to inches. 1.96. Yeah, so almost exactly 2 inches. I guess the ruler's right. I think I was maybe thinking the conversion from meters to feet or something like that. But yeah, 5 centimeters a year is roughly 2 inches a year, which is not very much. The fastest ones can go about 15 centimeters per year. The slowest ones go about 2 centimeters per year. And so they're not super fast, but over several 100,000 years, over several million years, you're creating quite a bit of new land there in the ocean basin. So the new land that they create, the new lithosphere, is hot and less dense, but it does cool and eventually subsides with age and distance from the system. And so that's what you're seeing actually back here. As it comes up, it's nice and hot, and so it kind of gets this expansion. You can see how thick it is. And then as it moves away from the ridge, it actually kind of condenses down, cools down, and ends up thinning out just a little bit. Okay, so they talk about seafloor spreading being the process by which new seafloor is created. Oh, wait, where this one? Continental rifting. So they said not all of your spreading centers happen in the ocean. There are some that happen on the continents. And actually, really quickly, let me show y'all a couple that are notable around the world. I looked this up for the other class because we got a couple slides ahead of y'all. Let's see. So, continental rift. They have continental rifts, and I should look up U.S. and go to images. And there's actually one up near the northeast. They're showing this one right here, up near the northeast and the Great Lakes, but that's not the one I'm most familiar with. The one I'm most familiar with is, where's it at? It's in New Mexico. Yesterday I found a nice image of it. Where was it? Why is it not here today? Why? Tell me. Oh, there it is. Nice. So view image. And basically right here, this Rio Grande Rift, Rio Grande, whatever. If you go into New Mexico, Arizona, you actually get to see, as you're driving, this very, very big, wide kind of valley. And it's filled with all of these tiny little volcanoes. Not very big volcanoes. They're not active now. But it's a lot of little like cinder cone volcanoes, which we'll talk about in a later chapter. But this is actually a rift where the United States started to tear itself apart because of plate tectonics. The western half kind of tried to pull away from the eastern and midwestern half. It obviously didn't succeed. Tearing a continent apart is very difficult, even for plate tectonics. Much more difficult than doing it to oceanic plate, but it does happen. And so this was a failed one that no longer has any activity at it. You can see the northeastern one that we talked about up near the Great Lakes that started but also failed. And then real quick, let's see. There's also some more in Africa. Let me see if I can find a nice picture of it. So this is basically it. It's right through Ethiopia, right on like the I forget the name of this, but they call it some sort of horn. They might just call it the African horn. But right through Ethiopia, right through Kenya. This little section on the eastern side tried to pull away from the rest of the continent. And you have this long failed rift area. You can see it on this image as well. So you can see they have a lot of earthquakes highlighted. They kind of give you some of the depths of the earthquakes. And with this topographic map, you can really see how it started to pull away. And this is actually like a triple rift center from, let's see if I can get a bigger picture. Here we go. From the Arabian Peninsula. Actually, let me make this bigger. Yeah, from the Arabian Peninsula. So you can see that the Arabian Peninsula obviously used to be connected to Africa. It used to be part of the African continent. And then quite a while ago, it pulled away from Africa, creating this sea right here. And part of that rifting event was also this third kind of leg of that you can see coming down here right through Ethiopia and Kenya, trying to pull this part away, although that failed. It might be still a little bit more active than the ones in the United States, but it doesn't look like it's going to complete itself, at least at this point. But the Arabian Peninsula is headed up this way, and eventually I believe this sea will close and it will collide with the Eurasian continent. So you can even see the spreading center kind of happening here as it continues to spread out. So pretty interesting active plate tectonics going on. Now, back to the PowerPoint. So we talk about continental rifting a little bit, your tensional forces pulling everything apart. Your brittle crust breaks into large blocks. You get a lot of earthquakes. Eventually things subside and the ocean is allowed to come in if you're close enough to the ocean. Obviously, we saw one in Arizona that's not close to the ocean, so it's not like the ocean flooded in there, but it is a lower elevation. So here's just a kind of a time-lapse image of what would happen in a continental rift. You take the continent, you get an upwelling of mantle material, which kind of pushes it up and bulges the land. The land has nowhere to go other than down because of gravity. And so gravity is actually going to start to help this pull it apart and get the motion started where these are separating. Eventually, as it pulls it apart, your crust is going to get thinner and thinner and thinner, even though you're kind of creating new crust because of that upwelling. And if the depression is deep enough and it's close to an ocean basin, you'll eventually start to get it to fill with water and kind of have a new inland sea created, or a smaller sea that's connected to the ocean. The further it pulls apart, the bigger your sea or ocean gets. So that's kind of the process that they have going on there. So now, instead of divergent plate boundaries, we're going to talk about convergent plate boundaries and what happens when plates smash together. So convergent plate boundaries occur when two plates move towards each other. You really have two different types, which I think we'll talk about in a second. You have continental and oceanic-continental collisions. There are also oceanic, but they kind of work the same as the oceanic-continental. So convergence rate is equal to seafloor spreading, and that's something I mentioned yesterday with the globe. If I have new material being created at one point, like the mid-ocean ridge, the Earth isn't getting any bigger. That's not what happens. So if anything is being created somewhere, it has to be being destroyed at a different place at an equal rate. If it's not destroyed at an equal rate, you will have more crust than you used to have, and that's not really how physics works. So you have to have convergence at an equal rate to seafloor spreading wherever you're talking about on the plate. So characteristics vary depending on the subducting crust, what type of rock you have, where it's at, what it's being subducted at. But subduction zones are what we call when a particular type of crust gets pushed underneath another one. I'm going to grab my globe real quick. Actually, maybe I'll just use the map, but I'll still grab the globe. So it all depends on whether you're trying to subduct oceanic crust under continental crust. Depends on what you have. They're going to point out that your oceanic crust is roughly 2% denser than the asthenosphere, and it's also more dense than the continental crust. The continental crust is less dense than the asthenosphere, and so generally your continental crust is going to float. It's going to be very, very difficult, almost impossible to push the less dense continental crust down underneath the asthenosphere and get it to melt in the mantle. Where the oceanic crust, it really doesn't need a lot of effort. It's already more dense than the asthenosphere. And so if you give it a little shove or start it in the right direction, gravity is just going to do the work of that kind of motion and continue to pull it down. So the oceanic crust is what's going to be subducted in your subduction zones. The continental crust is not. So at your subduction zones, you get your deep ocean trenches. And this is actually, does anybody know the name of the most famous trench where the biggest earthquakes happen near Japan? No. Shame on y'all. It's the Marianas Trench. Google Earth. And so where the Pacific Plate is being subducted underneath Japan, Earth, you have the Marianas Trench. This is the deepest place on Earth, the deepest part of the ocean. Famously, some rich people have gone and explored it because you have to have crazy, crazy submarines to go down there. But very, very deep, and it creates very, very large earthquakes. Here's the United States. And here's Hawaii. Look at the Hawaiian chain extending all the way out and coming up towards Russia. And if we come over here to Japan, you can see this trench already. See this really deep black line. This is the Pacific Plate being pushed underneath the Eurasian plate right here. And this subduction zone is where you get your really, really big earthquakes that plague Japan all the time. Why they have bad tsunamis. And it is absolutely like the deepest place in the ocean. It's pretty crazy. So this is the Marianas Trench. And I'll kind of explain what happens there in just a second. I want to see if the book does a very good job of illustrating it before I bother to draw. If I bother to draw it on the board. That was very disappointing. There we go. Okay, I fixed everything. Nobody panic. So let's see. Your deep ocean trenches are a result of subduction. You can see that they're long and linear from the image we just saw on Google Earth. The angle of subduction varies. It depends on whether it's very flat or very deep as to how deep your ocean trench is going to be, which also depends on the crust. If you have very dense oceanic crust, it's probably going to be a little bit deeper. If it's not dense and it's kind of going against another oceanic crust, maybe it's a little bit shallow. These pictures aren't super big, so I will actually draw it on the board real quick. But what you have three different types of collisions that can happen here. You have oceanic crust being subducted underneath continental crust. The continental crust is always going to win. It is less dense. The oceanic crust is more dense. As it gets pushed underneath, it's going to hit down into the mantle. As it goes through the asthenosphere, it's going to go into the mantle. It's going to start to melt. And the melted things, just like in a lava lamp, just like we talked about with igneous rocks, the hot melted things are less dense, heat rises, and so your melted material is actually going to rise back up and feed on land volcanoes. These are the types of volcanoes we have in the Pacific Northwest in Washington State and Oregon, and even all around Alaska and Alaska's giant peninsula. These volcanoes get fed by the melting oceanic plate. Now, you can have the same thing if you have two oceanic plates subducting beneath each other. So you have oceanic plate being subducted underneath a section of oceanic plate. You get the same melting, but the volcanic material comes up in the ocean instead of coming up on land. And so this kind of volcanic material is going to be similar to what you have in Japan. So Japan is on oceanic plate. It's part of the Eurasian plate, but the Pacific plate's being subducted underneath, and the volcanic material doesn't quite come up on land. It comes up right underneath Japan. And then your third type, so we have oceanic continental. we have oceanic, and then we have continental, where two continental plates collide. And like I said before, this is more like a car wreck. Nothing's going to go underneath. They're just going to smash together at the same level. And when you have that smashing, you have stuff that essentially gets pushed upward. And so you have a mountain range that's created here by your smashing together of your oceanic plates or your continental plates. Now, just real quick, I want to show y'all what happens. Well, let me just make sure. I swear there were good images of this. Okay, fine. I guess not. So let me take this so the people online can see. Hello, online people. How are y'all today? Graded some labs yesterday. Some of y'all haven't been doing your labs. You haven't been completing them. Okay, basically, you have your oceanic crust or your continental crust a little bit. Let's just say it comes out here. This is continent. And then you have your oceanic crust, which comes down and starts to get subducted. Right? Nice. What's going to happen here at this point is actually very important. First of all, anytime you have subduction, you're going to have that deep ocean trench. Right where my arrow is pointed, it gets very deep, deeper than anywhere else in the ocean. And this is also what creates your earthquakes around these areas. And so you can see that you have contact between your continental crust and your oceanic crust. Do rocks rub together really smoothly? No. Especially an entire continent or an entire ocean basin full of rocks. They're going to catch, they're going to have friction together, and they're not going to slide very easily. And so over time, in between your earthquakes, what happens is your oceanic crust continues to move downward as gravity pulls it and as the natural plate tectonic motion continues. Your oceanic, or your continental, let's see if I can do this and make it actually somewhat relevant. Your continental plate is actually going to get pulled down like that. That's a little bit better. Yeah, it's going to get like a little flex there. Let me do it like that. That illustrates a little better. So it's going to get like this little flex here, and the oceanic plate's going to pull it down at the end as it goes through. And so I actually used to do this better with my hands, which it doesn't look as nice. But so this is like your continental plate. Here's the oceanic plate, and the oceanic plate is being subducted, and you get like a catch. It starts to get friction, and it starts to catch. And as the oceanic plate keeps going, it pulls that continental plate down with it. And so that's what builds up your pressure from your earthquake that happens. And so as it pulls it down, it gets that flex. Eventually, something's going to slip because it can't pull the continental plate all the way down with it. So eventually, something's going to slip. And what happens is you have that pressure released, and it pops back up. That's what gives you your big earthquake. That's also what changes the seafloor level and causes large tsunamis, especially in areas like Japan, which are very similar to what we're talking about here. Did everybody see that? Yeah. I saw that on the video. Nice. So it's very important to study this kind of plate tectonic interactions because we want to understand the earthquakes. We want to be able to predict them better, and to hopefully help people safely navigate them and not really have it be as devastating as it usually is. So let's see. They talk about subduction. The continental lithosphere is less dense. Yeah, we went over that. Yeah, partial melting. No, that's a part of that partial melting that feeds those volcanoes is because water from the descending oceanic crust triggers partial melting. That's actually something that took me a while to get used to in geology. In our brains, you think if you take a hot rock and add water to it, it's going to be less likely to melt, right? Because for us, water cools things off. But in rocks, water is what's considered a volatile. And so if you add water to a really hot rock system, it's actually more likely to make it melt. And so we'll talk about that also in volcanoes. They call them volatiles, and water actually aids the melting of rock as opposed to inhibiting it. So there you go. They're showing you the ring of fire here. So these are your convergent plate boundaries all around the Pacific Ocean. And there are just volcanoes pretty much everywhere around there. So you have the South American one. There's not a lot along this coast of North America. There's a little bit here and there. So up near Washington, you have a few. But we have the what's the name? The San Andreas Fault, which is more of a transform fault in California and a large portion of our western seaboard. So that kind of protects us a little bit from those volcanoes and those really, really strong earthquakes. But eventually that will probably change and we will get back to subducting. So Central America down here has subduction zones all along this long, what would you call it? It's not a peninsula. It's more like an island chain. This island chain that is this very long hook that is Alaska. And I don't even know how far this goes. Like, I doubt all of this all the way over here is Alaska. But all of this is kind of connected to the same feature off of this little hook of Alaska. All along Japan, the Japanese Marianas Trench, you have volcanoes, you have earthquakes. It's just a very active place as far as subduction is. So that's why the Pacific Ocean in particular is considered the ring of fire, because you have a large portion of the world's volcanoes all around that area. What are they showing us here? Mount Hood in Oregon. This is a volcano, and they're just giving you an example of the melting that goes on when you have a continental oceanic plate interaction. So the oceanic plate is getting pushed underneath the continental plate. It's being subducted down, being pulled down by gravity and density. As it comes down, because it's kind of saturated with water, you have melting that starts to happen, or partial melting. That melt comes up to the top because hot, dense things come up to the top. And it feeds these volcanoes like Mount Hood, Mount Rainier, Mount St. Helens, this entire kind of chain of volcanoes in the Pacific Northwest. So if you've ever had a chance to visit them, they look pretty nice. You have nice, very pointy mountains, which really, when there's not a lot of other mountain ranges around them, you can know that this is a volcanic mountain because the way that it builds up with really no other mountain chain is definitely related to volcanics. So let's see. One slab subducts under another at oceanic convergent boundaries. You get that same volcanism that happens, but instead of the volcanoes being on land, like in Oregon and Washington, they happen out in the ocean. Your volcanic island arcs, which would be similar to Japan. Or here, in that long stretch of islands coming off of Alaska. They don't name this. I'm trying to remember some of the volcanoes in Alaska. They have some pretty big mountains. In fact, the biggest mountain in the United States, I believe, is in Alaska. Actually, no, they name a bunch of them right here. I don't know that any of them are these, but they name a bunch of these volcanoes as you come out along this little arc. And the reason is the Pacific plate's being subducted underneath right here. And so as it melts, as it goes down, it feeds these little volcanoes there. So what is it, all that Alaska? Someone look up and tell me where Alaska ends. Do we own way out here to there? Does anybody really own Alaska, or does Alaska own you? So I feel like the flag, or the way we look at it, probably ends like somewhere over here, maybe. What if there's no hard border?
This is all
it's just
history stuff.
I know, yeah. Where does Alaska end?
It's like the end of a dispute.
Where the bears stop attacking you, you're now out of Alaska. Yeah, it's not a big deal. Yeah. That could be, especially imagine who are you asking, a U.S. publication or a Russian publication? Probably depends on where that line is. Maybe it's right in the middle. Okay, so just remember, whether something gets subducted or not is all about density. And we're talking about density and floating versus sinking. you're talking about buoyancy. So your continental crust is actually buoyant. It floats compared to the mantle and the asthenosphere and the oceanic plate. And so continental crust is not going to get subducted. It's going to float all the time, which is why the continents are very old and the oceanic plate is not. Can I zoom in on this? Let me see. This is actually pretty important. I want to highlight this for everybody to see because there will probably be a test question or two on it. Can I zoom in here? Or maybe just let me look it up. India plate tectonics images. Yeah. And that's not even that great. Let me see if he has it. This is actually from my old professor, and I feel like maybe he doesn't do as much anymore, and the website's not quite as up to date as it should be. Tectonic evolution of the Indian Ocean. Oh, there's no link here. India with Asia. No. To run animation, drag mouse across image. There is no image. No. Let's see. What? Oh, it's right here. Videos. Maybe. No, here. This one. Yeah, this is SCOTEs. They're both SCOTEs. Nice. So I can find it on YouTube instead. Okay, we like this. Okay, so this is the current. Now, actually, let me stop this. Dang. Okay. When I get taken down by YouTube, block this out. If you're at home and you want to watch this, go onto YouTube and Google Indian plate tectonics and go to videos and look for this Christopher Scott's video. And I might even have to put this at the end of the video because I have to pause it now. I'm going to resume. So hopefully that doesn't get taken down by YouTube. But when they show this little segment right here, this picture doesn't quite do it justice to show really how fast India was moving up and it collided into the Eurasian continent. That is how we got the Himalayas. You can see India coming up. There's still an ocean basin here. And then the collision happens. And they're both continental plates, so neither one's going to get pushed downward. They both smash into each other, and essentially stuff gets pushed up. Some of the Indian plate gets dragged down a little bit, but it's not going to get fully dragged down. It's just too buoyant to be able to do that. So instead, you get the mountain building that happens and deformation of a lot of rocks. So what are the characteristics of each of the three types of convergent boundaries? Oceanic continental is going to be your oceanic plate subducts. So you have a subduction zone, you have deep ocean trenches, and you have volcanism on the continent, continental volcanism, creating these volcanoes similar to the Pacific Northwest of the United States. You have oceanic, which has pretty much the same thing. You're going to have subduction zones, you're going to have deep ocean trenches, and instead of continental volcanic arcs, you're going to have island volcanic arcs that happened out in the ocean, similar to Japan. And then continental collisions are going to result in mountain building, deformation, and a lot of sedimentary and even metamorphic rocks because of all that heat and pressure. So that's going to be like India slamming into Asia. Yeah, we still got a couple minutes. Let's see how far we can get. What am I on? Slide 30 of 51. That's good. We can finish this tomorrow. So transform plate boundaries are going to be the different ones. We talked about divergent. We talked about convergent. Now we're going to talk about transform. They essentially move side by side and don't really have any creation or destruction. It's just moving of plates and releasing of tension, essentially. So they slide horizontally past each other. Faults on these plates are called transform faults. Nothing is produced or destroyed. It just kind of connects spreading centers or offsets different ridges. It's just kind of like a stress reliever in these big areas. The San Andreas fault is a transform fault, but I kind of drew this yesterday on the board. So this is probably a better picture of what I was talking about with the transform faults. You have spreading right here, spreading right here, spreading right here. But because these are offset, you have a couple areas that go side by side right past each other. So that's where your transform faults are going to be to kind of relieve that tension and relieve that pressure. And you can see all the transform faults all the way up the Mid-Atlantic Ridge, just relieving all that tension and pressure. So there are a few transform faults that cut through the continental crust. Their example here is the San Andreas fault that cuts through California. Here's a nice river, and you can see that it's been offset by the San Andreas fault. As the fault moves this way, it's pushed this part of the river to the left, that part of the river to the right. And now the river, here's an actual picture of it, has to compensate by running along the fault. Let's see, testing the plate tectonics model. So this is some evidence for plate tectonics. We get evidence for this from deep sea drilling projects. They collect sediments and oceanic crust. They're able to date fossils in the sediment, and they see that the sediment age increases with distance from the ridge. And so that's actually interesting. I don't have a picture on the board to show you, but you have a mid-Atlantic ridge in the middle of the ocean. They see that the sediment right next to the ridge is very, very young, even when they drill down into the crust. Very, very young sediment toward the ridge. The further away you get from that ridge, the sediment gets older and older and older. The fossils get older and older, which tells you that that rock has been around a little bit longer than the stuff in the middle. And so if the stuff in the middle is younger, the stuff on the outside is older, you can kind of see the way that that mid-ocean ridge is producing more new crust there in the middle. And again, we mentioned this before, the oldest seafloor is about 180 million years old. And so here's a good example. Right towards the middle, brand new crust, hasn't been around very long, not very many sediments, and the sediments are pretty young. The further away you get from that spreading center, the sediments build up and get thicker and thicker and thicker. And it's not until you get to the very outside that you start to get really old sediments here, because that crust is the oldest compared to the entire basin range. So taking these drilling samples has really given us a better view of how that works. Nice. This is a good place to leave off. So tomorrow we'll talk about the Hawaiian volcanoes and hotspots, which you will see in the lab that we have. So thank you, online people, for joining in today. I hope everybody has a nice day, and I will see y'all tomorrow.